All right, so now let's take a look at the last set of Lewis structures. These are the most complicated ones because they have what's called resonance involved, meaning basically you have to draw multiple structures to answer the problem. Okay, so let's sort of walk through an example of why that might be. So this is ozone O3, and if I followed my procedure that I laid out in the last video, I would have gotten to this structure right here, where I have my lone pairs to satisfy my constituent, I have the single bonds attaching the constituent atom to the central atom. My octet of all my constituents has been satisfied by adding those lone pairs. But now I get to this step where I check to make sure everybody has a full octet, and this oxygen in the middle doesn't. It's got 1, 2, 3 pairs or 6 electrons total. It doesn't have 8, right? So then what do I do? Remember, what I would do is I would rearrange electrons, but notice that because of like the symmetry that's going on here, I can either choose this pair of electrons, move it down, form a double bond, or I could choose this pair and move it down and form a double bond, right? There's sort of ambiguity. Do I choose the left carbon or the right carbon? When you find a situation like that, you actually have to do them both. And we say that they are in resonance. So you draw this little double-headed arrow that would separate these two molecules. These are resonance structures. Okay. And what's kind of wild is that it turns out that in the world of chemistry, this molecule never looks like one of these structures or the other. Right? It's actually that pair of electrons is jumping back and forth between those two oxygens. So that's why we have to include both structures and not just one. Our polyatomic ions that we saw also will have resonance structures. And it's sort of the same idea of one of these oxygens has a double bond, but do we put it on that oxygen, or that oxygen? You got to pick, right? So because it's arbitrary, we'll include all of them. So let me show you how we start from scratch in terms of how we got these resonance structures for the carbonate ion. Okay, so we're going to go through the procedure of how we do the Lewis structure sort of from scratch here. So first step is to calculate total number of valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. We have carbon and oxygen, right? So this would be carbon has 4 valence electrons for the carbon plus 3 times the 6 valence electrons for the oxygen plus 2, and this comes from this charge, right? So my charge tells me I have 2 extra electrons. So when I'm calculating the total number of valence electrons, I need to make sure to add that to the total. So 18, 22, 24. So we have 24 valence electrons total for this structure. Now my second step, as always, put the less electronegative atom in the center and put the oxygens, the constituents all around. We're going to draw single bonds to each one of my substituents. That gets rid of 6, so we're left with 18. We have to then satisfy, so now we're at this step here. Are there any electrons remaining? Yes. So we're going to complete the valence of all the constituent atoms. All right, so 1, 2, 3, 4, 5, 6 completes its valence. 6 completes that oxygen's valence, and 6 for that oxygen. So that means 18, we're left with 0. So all of our electrons are now down on the board, okay? So do you have any electrons remaining? No. Now we have to check if all of our atoms have a full valence, and we see that we have this problematic carbon in the middle. It's got 2, 4, 6 electrons, so it does not have a full valence. So now I'm going to get to this step here where I'm going to remove a lone pair from the constituent atom and replace it with a higher order covalent bond. Well, notice that it doesn't matter which oxygen I choose. Any one of them will satisfy it, right? So let me actually copy this real quick. right? And by that, I mean, if I have taken this pair of electrons from this oxygen and moved it down here, forming a bond, that would work. Or I could have taken this one, moved it down here, formed a bond. That would have been the same thing. Or I could take this one, move it over here and form that bond again. Either of those moves would work. So in that situation, when you find yourself in that situation, you got to do all three of them. So I'm actually going to move this over here. Okay. On the first one, I'll take it off of this leftmost structure. On the middle one, it's going to be from the top. And from this one, I'll take it from the rightmost oxygen. Okay. And all three of these structures will exist in resonance, right? So again, it's not like that pair of electrons is going to sit between one carbon and oxygen. It's actually going to move around to all of them. It's kind of bizarre. The other thing that we're going to do, because this structure has a charge associated with it, it has this net charge of -2. The way that we do that with our Lewis structures is we put brackets and then the charge around. Okay, so if I asked you for the Lewis structure of carbonate, it would actually require you to draw all three of these structures in resonance with one another. That would be the correct answer here. One other thing that I'm going to mention, because you'll see it, although we're not going to deal too much with these structures that have these expanded octets, is if you look at a periodic table, everything in the first two rows specifically, actually, I guess these abide by the octet rule strictly, right? Carbon will always have 8 electrons to complete its valence shell, same as fluorine. I guess I'm going to leave off hydrogen and helium. Remember, we said that they require 2 valence electrons. The purple one, I said those are the normal ones, require 8 valence electrons. There's 2 other exceptions we learned about. One was beryllium. Beryllium likes to have 4 valence electrons. And then lastly, boron. Boron likes to have 6 valence electrons, okay? Now, most every element bigger than that, right? So like these ones down here, they also like to have 8 electrons in their valence shell. So they'll be perfectly happy if they have 8 electrons to fill their valence shell. But, actually silicon's included, but they can accommodate more. So they can accommodate as many as 12 electrons. These are called an expanded valence. Again, I'm not going to ask you to draw the Lewis structure of any expanded valence compounds, but you will come across them. You'll see them already drawn. And so I just want to explain. So for example, in this phosphorus pentachloride, the phosphorus has 2, 4, 6, 8, 10 electrons in its valence shell. And the sulfur hexafluoride, sulfur has 2, 4, 6, 8, 10, 12. So there are instances where larger atoms, ones that live below the second row of the periodic table, can accommodate more electrons into their valence. Again, I'm not going to ask you to draw these structures, but you will see them. Okay. If we want to do just another example here, the nitrate ion, again, just kind of working from scratch. This is one that we hadn't seen the correct answer for, so I think it's a good one to go over. Again, step 1, calculate the total number of electrons in its valence. So we're going to label 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has 5. There are 3 oxygens, each with 6. And then remember, I have to add that 1 to account for the net charge on that nitrate ion. So this would take me to a total of 18, 23, 24 again. Okay. Put the less electronegative atom in the center. That would be nitrogen. Decorate it with the oxygens around. Draw single bonds and subtract from the total. 2, 4, 6. That leaves me with 18. So now I'm here. Complete the valence of all the constituent atoms, subtracting from the total. So that means I'm going to add 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. All right, so that gets rid of all my valence electrons. Good to know. Okay, so now I'm at this step. Do all the atoms have a full valence? No, the nitrogen in the middle is missing a pair. Is missing 2 electrons. It only has 6. So now we find ourselves in that familiar situation where it doesn't matter which oxygen I would grab it from. I could, in theory, grab it from any one of them. And because of that, I need to make sure to include all 3. I'm going to subtract, get rid of this just to make some room here. All right, so I have to do it to all 3 oxygens. That's how I know that there are 3 resonance structures. So for this one, I'm going to move this pair. For this middle one, I'm going to move this pair. And then for this last one, I'm going to move this pair. Okay, and remember, these are all in resonance with one another with those 2-headed arrows. And again, because this molecule has a net charge, I need to be good about putting the brackets around it. Okay, so this would be, again, all of this together would be the correct answer for the Lewis dot structure of the nitrate ion.